Hello. This will be a demonstration of Proposition 18 from Book 9 of Euclid's Elements, which says, given two numbers, to investigate whether it is possible to find a third proportional to them. We're given two numbers, A and B, and the task before us is to investigate whether it is possible to find a third proportional to them. That is, whether there is some number such that A is to B just as B is to this number. If such a number exists, then it is a third proportional to A and B. Now, our two given numbers A and B, they are either prime to each other or they are not prime to each other. If they are prime to each other, then we know from Proposition 9.16 that there can be no third proportional to them. For that proposition, 9.16 tells us that if two numbers are prime to each other, then the second is not to any other number, just as the first is to the second. Or in other words, there can be no third proportional to two co-prime numbers. So if A and B are prime to each other, if they are co-prime, then we know that there is no third proportional to them. But say that they are not co-prime to each other. What we're going to do then is we're going to create the number C, and the number C will be the square on the number B. So B squared, or B multiplied by B, makes the number C. Now, it is either the case that the number A measures the number C, or it does not measure the number C. If it does measure the number C, then let it measure it according to the number D. We'll create the number D such that A measures C according to D. Or in other words, A multiplied by D makes the number C. But we also know that B multiplied by B makes the number C. That's how we made the number C in our third step. So we have two products which are equal to the same number. So common notion 1 tells us that they are the same with one another, so that the product of A and D is equal to B squared. Now by Proposition 7.19, we can turn this into a proportion and say that A is to B just as B is to D. Now, from this statement, it obviously follows that the number D is the third proportional to A and B, because A is to B just as B is to D, therefore D is the third proportional to A and B, and so if A measures C, or in other words, if A measures the square on B, then a third proportional will exist to our two given numbers, A and B, and it will be the number according to which A measures the square on B. But say that A does not measure C. What we want to prove from this is that there is no third proportional to A and B. For suppose that there is. Suppose that there is some number D, such that A is to B just as B is to D. Now again, by Proposition 7.19, we can turn this proportion into a statement about the equality of two products. So because A is to B just as B is to D, we know the product of A and B is equal to the product of B and B, or B squared. And we know from our third step that B squared is the number C, so the product of A and D is the number C. But from this, it obviously follows that the number A does in fact measure the number C. It measures it according to D, because if A multiplied by D makes the number C, then A measures C according to D. But this is contrary to the hypothesis of this case, which is that A does not in fact measure the number C. And so, were there some third proportional in this case, the number A will both measure and not measure the same number C, which is obviously impossible, and so we can conclude that there is no third proportional to A and B if A does not measure C, or A does not measure the square on B. These being all the possible relationships that A and B can have to each other, we are therefore done with the proposition, therefore, etc. QED. You'll notice, of course, that this proposition is not only about investigating whether or not it is possible to find a third proportional to two given numbers, but figuring out what exactly that third proportional is. And as I stated before, the third proportional, granted that it does exist, is that number according to which the first number measures the square on the second. Before I end the video, I'd like to go through a few cases of how you would apply this proposition. Say we have two numbers, 4 and 9, and we want to know if there is some third proportional to them. Well, our first question is going to be, are they prime to each other? Are 4 and 9 prime to each other? Yes, they are. So this proposition tells us, or rather proposition 9.16, tells us that there is no third proportional to these two numbers. But say that they are not co-prime to each other. Say instead we have something like 4 and 6. Is there a mean, or not a mean proportional, but a third proportional to these two numbers, such that 4 is to 6, just as 6 is to this number? Now, we know, at least by hypothesis of this case, that 4 and 6 are not prime to each other. They do have a common measure. That common measure is 2. So our next step is going to be, does 4 measure 6 squared? Well, what's 6 squared? 6 squared is 36. Does 4 measure 36? Yes, it does. And more importantly, it measures it according to 9. So what this proposition is going to tell us is not only is there a third proportional to 4 and 6, but it's also going to tell us that that third proportional is the number 9. So 4 and 6, there is a third proportional. But say it's not 4 and 6, say it's 6 and 10. Now, are 6 and 10 prime to each other? No, they are not. Just like the case before this, they have the common measure of 2. So our next question is going to be, does 6 measure 10 squared? Well, 10 squared is 100. Does 6 measure 100? No, it does not. So this proposition is also going to tell us that there is no third proportional to 6 and 10. So this would be how you apply this proposition. You would first ask, are our two given numbers prime to each other? If they are, then we know automatically that there is no third proportional to them. But if they're not, then the next question is going to be, does the first number measure the square on the second? If it does, then there will be a third proportional. But if it does not, then there will not be a third proportional. One last thing I would like to mention before I close out this video is a question that maybe you'll be asking yourselves if you remember book 6 of the Elements. Because in that book, that was the first time we saw the language of third proportionals. We saw it in proposition 6.11. That proposition was about finding the third proportional straight line to two given straight lines. But before we did that proposition, we did not have to do something like this, where we had to investigate whether or not it is even possible to find a third proportional to any two given straight lines. We just took that as given, and we found the third proportional accordingly. In other words, a third proportional always exists to two straight lines, but it does not always exist to two numbers. I would like to briefly explain why exactly that might happen. And the reason that that might happen is because you can do operations between two numbers where the result will not necessarily be another number. But this is not the case for straight lines. No matter what you do to two straight lines, you can divide them by each other, multiply them by each other. No matter what you do, you'll always end up with another straight line. Let's take as an example of numbers 4 and 7. Now, if we ignored this proposition and just took it as given that there is a third proportional to 4 and 7, we also know how to find that third proportional. It will be 7 squared divided by 4, or in other words, the number according to which 4 measures the square on 7. So that would be, 7 squared is 49, so the third proportional would in theory be 49 divided by 4. But this is not a number, at least not in the Euclidean sense, or as we would say nowadays, it is not a natural number, but rather it is a ratio. And so you see that not all operations we can do on two numbers always result in another number, which is why this proposition is necessary, because it's not guaranteed that if we divide the square on the second number by the first number, we'll end up with another number. But with straight lines, we can do that process just as well, and we know that there will always be a straight line by the end of it. That's all I've got to say about this proposition, so I'll end the video here and move on to proposition 9.19.